In this video, I'd like you to learn about how the three laws of thermodynamics were formulated and be able to define each of these laws as they apply to the exchange of energy in a system. The three laws of thermodynamics date to the age of steam, as scientists and engineers grappled with making more efficient steam engines that would later fuel the Industrial Revolution. The birth of the steam locomotive in the early 1800s led to interest in determining how to use energy more efficiently. Born during this time of innovation, William Thomson, who later became known as Lord Kelvin, worked on formulating various laws or principles of energy. He is equally famous for helping to lay the first telegraph line across the Atlantic Ocean, allowing electronic communication between Europe and the United States in 1866. Lord Kelvin was an original steampunk scientist and worked on formulating principles to govern how energy is exchanged in a system. He worked hard to put these into simple laws, which were backed by numerous experiments. These laws have changed somewhat over the 150 years that he first proposed them, adapting new discoveries and evidence, but hold well and serve as fundamental principles in physics today. The transfer of energy from one form to another and one body to another is the subject of three laws of thermodynamics. The first law of thermodynamics is the principle of conservation and transformation, which basically states that energy is neither created nor destroyed in a system, but merely changes from one form to another form. For example, sunlight is converted through photosynthesis to make a plant grow, while as humans we eat the plants and convert that energy into energy to think and take a class and, well, watch this video. Hence, energy has never just been spontaneously created. It was transformed from one energy source to another. But where did the energy come from? In the sun. Einstein's discoveries later modified the first law of thermodynamics, with his famous equation of E, energy, is equal to m, mass, times the speed of light, c, squared. Thus, changes in the mass produce large amounts of energy. This change in mass can be either the splitting of atoms, fission, which decreases mass to release nuclear energy, or increased mass through fusion, which is what the sun does by smashing atoms together, which releases energy. We'll talk more about the sun's energy in the following video, but with this modification, we will talk of the first law of thermodynamics as we speak of a system in which the mass is held constant, where there is no nuclear fission or fusion occurring. A good example of the first law of thermodynamics is losing weight. The more you eat, the more energy is stored in your body as fat. Thus, to increase weight loss, energy must be used in the form of work, exercise, in this case a unit of 1 at least. Thus, energy is not stored as fat, but used in the body. It is a simple principle we observe in our daily lives. Energy that is used in our daily lives is transferred from one form to another. Such transfers of energy is what provides all the dynamic interactions in the Earth system. Energy cannot simply appear. It must ultimately have a source. We'll talk about the major sources of Earth's energy in the following two videos. The second law of thermodynamics is called the efficiency and enthalpy principle, which states that energy always changes from a more useful, more concentrated form to a less useful, less concentrated form. In other words, energy degrades over time and with each transformation. The second law of thermodynamics documents that energy transfer is not always 100% efficient. There is always a loss of energy when it is converted from one form to another form. Over time, this loss of energy results in what we term enthalpy. Entropy is simply the measurement of disorganization over time. You might have experienced this in your room, that if you don't clean the room will become disordered. To clean the room means that you must put energy into cleaning and achieve a more ordered state by not having dirty clothes on the floor, but neatly folded away or hanging in your closet. It's important to note that ultimately what dictates how ordered the state of a system is in is derived from the energy source and the amount of energy entering the system, and how this energy is transformed or transferred into the work. Thus, a decrease in entropy requires energy, while increase in entropy does not require any additional energy. In some systems, organization increases because there is an energy source to increase order in the system. However, the universe as a whole is becoming more disordered over time. This idea of a universe completely disordered, completely cold, led Lord Kelvin to think of a temperature so low that everything would freeze and there would be no energy at all in the universe anymore. The third law acknowledges this fact, that there is an absolute zero temperature, in which it can't get any lower. Temperature is a measure of heat, the vibrational motion of particles. The higher the temperature, the more the particles bounce around. At the cold temperature of absolute zero, all motion would cease. Kelvin and other scientists set out to determine the absolute lowest temperature and referred to this temperature as zero. This is called the Kelvin scale, named for you-know-who. In the Kelvin scale, absolute zero was found to be negative 273 degrees below the temperature that water freezes on the Celsius scale, which is based on the boiling and freezing temperature scale of water. Hence, negative 273 degrees Celsius is equal to zero on the Kelvin scale, and nothing can get colder than negative 273 degrees Celsius. Einstein and other later physicists learned more about the makeup of atoms, which we'll talk about later in the next chapter. They showed that even at a temperature of zero on the Kelvin scale, electrons would still encompass the nucleus of atoms and spin. This tiny, minute bit of energy would hold the electrons to the atoms and hence would not completely freeze still. This tiny bit of energy is called zero-point energy. We'll not spend time discussing zero-point energy, but understanding how matter behaves at absolute zero is currently at the cutting edge of physics and chemistry today. As we get closer to achieving absolute zero in the laboratory, we might discover some very interesting facts about matter and energy. At temperatures close to absolute zero, electrons are easily transmitted and certain substances become superconductors. Another strange feature of supercold matter is that magnets produce the mesmer effect, lifting objects by enhanced magnetic fields from those electrons at very low temperatures. If the electrons are completely separated from the nucleus of an atom, we call these stripped-off electrons plasma. We'll talk more about plasma in Chapter 3 when we discuss matter. You've now been introduced to the three laws of thermodynamics. The first law, conservation transformation. The second law, efficiency and enthalpy. And the third law, the existence of absolute zero. Be sure to review these in your textbook. In the next video, we'll take a look at the two major external energy sources for the Earth system, the Sun and the Moon.